Okay, so good day everyone. In the previous video, we have discussed about assessing model accuracy, and we have discussed mean squared error, which is one of the most common regression metrics. Okay, so for today, we are going to discuss about the bias variance trade-off. But before that, let us quickly go over about what overfitting and underfitting are. So when we are building machine learning applications, we are more concerned with the test na dataset rather than the performance on the training na dataset. So there are cases wherein you train your model and you get an output, let's say a 99% accuracy. But when you test it on a new unseen na data or a real world na data that wasn't used during the training, your model will perform poorly or will give you very low na accuracy. Okay, so that is an example of an overfitting. So we have here an example of a plot of the training and the testing error. So the red line represents the training data error, while the blue line represents the validation data error or the test error. So we can see that even if the training error is consistently decreasing, the error on the new data set is increasing, which means that your model haven't find the proper pattern and just randomly predicting the values for this test data. Okay, so what happens is the model has overfit. Okay, when we say overfitting, it could happen because you have trained the model for so long, or the model might be too complex such that it learns including the noise or the randomness in the data. So as you can see, the plot for the overfitted model is squiggly, okay? And the line or the fitted line is very close to the data points. Right? So we can say that this kind of model has a low bias. Okay, so let's have an example. So what does low bias actually mean? So the bias refers to the error that is introduced by approximating a real life problem. Okay, and the bias is actually the difference between the predicted and the expected value. So the model makes assumptions when we are training on the data that is provided. Suppose we have the train errors, and the train errors on some samples gives you 0.02%, 1%, 2%, and 0.5% only. So we can see that the bias is small, okay? The bias is very close to 0. Or in other words, the difference between the predicted and the expected value is low. But when you test the model on the unseen test data, the test errors are increasing. So you can see that in the train error, we barely have 3% of error, but in the test error, we have 5%, 90%, 25%, or 60% na error. So we can see that the test errors is highly variable or spread out. So we can say that predicted values are highly spread out. Okay, so we can say that the variance is high. Okay, and so when the model starts to overfit, then we must unlearn what we have learned. So as I have mentioned before, an overfitted model also learns including the noise or the randomness in the data set. And the model, in order for it to perform well, it must unlearn those noise that it has learned. All right. So now we also have another problem, which is the underfitting. So in the previous slide, we have shown you a complex model or a model with low bias, such that the fitted na line is very, very close to the data points. Okay, so it almost learns every angle or every data point in the data set. And this is caused by training the model for too long or for having way too complex the model. And we don't want that. So what we can do is to unlearn some of those patterns, and we could simplify the model. Okay, but having a way too simple na model is also not a good also not a good model. Okay, so we can see here in the underfitted na line, wherein obviously the data points are not linear. Okay, the data points are obviously curved. However, we assume that the shape of the data or the shape of the estimate is linear. So having such assumptions will provide us a high na bias, okay, or high bias na results. So even if we find for other na fits or other line na fits, still the model will perform na poorly, because obviously our assumption did not capture the actual na shape of the data. Okay, so this is an example of underfitting. And this happens because the model might be too simple to classify the underlying data. Okay, and having this kind of assumptions will result to high bias na errors. Okay, so if we observe our train errors, high bias means that the difference between the predicted and the expected na value are also large. So, and that happens both on the training set and the testing set. So if we see the errors in the training set, you can see that, let's say the errors are 80%, 85, 82%, or 82.1%. So what we want is an error that is close to zero. But we can see that even just training, the errors are already high. So we can say that having a high na difference between the predicted and the expected, we have a high na bias. Okay, and if we test it, then we can see that the prediction errors for these test na data are also very high. However, unlike the overfitting na problem, there is a low na variance on the test na errors. In other words, the errors are very close to each other. So if we observe that in a bullseye diagram, if this is our target, if this is our expected na value, and this is the predicted na values lie. So we have a high na gap between the expected and the predicted, but we can see that the points are close to each other. So we can say that an underfitting problem has a high bias and a low na variance. Okay, so now how can we find the optimal na model? So we don't want a too complex na model. We don't want a too simple na model, but we want a good fit na model. A model that can generalize to new and seen na data. So suppose we have the train errors, and the train errors should have, or ideally have, low na train na errors. Okay, or that means we want to have low bias or low or small na difference between the predicted and the expected na value. And we expect that if we test model on the unseen na test data, the test errors should also have ideally low na errors or small na errors. Okay, and of course, we want that the errors are close to each other or not highly spread out. In other words, we want a low na variance and a low bias. And if you can see in this diagram, and our target is the red na point. Okay, so we can see that the data points are close to each other or huddled with each other and are also very close to the target. So this is the fit that we want.